Hello again. This is Math 2245 coming to you from the College of DuPage. The title of this lecture is Leontief, Low Stakes Assessment. This is someone's proper name. As always, please be an attentive listener while watching this video. So I'm stating the LSA first. Some context will follow that can help you to solve this. So suppose a four-sector economy presents the following internal consumption matrix. So here's the internal consumption matrix. It's a 4x4 for a four-sector economy. And an external demand vector, and this is 10, 20, 30, 40, is the external demand vector. Now what you're supposed to do with this is find the production vector to satisfy this demand, accurate to 4 decimal places. And I'm allowing you to use technology, and with these numbers you really probably should be using technology. And so part A, I want you to just invert the appropriate matrix. And then, and actually it's not this one, it's one related to that, but invert the appropriate matrix. And then part B, I'm asking you to invert the appropriate matrix, but using the power approximation with the powers going up to 5. And then compare the two and discuss your observations. Now I did allow you to use technology, and so I'll talk just a little bit about technologies over here. The frowny face is that over my objections, the math department canceled our access to MATLAB. Now MATLAB actually stands for Matrix Laboratory, and this is something that maybe you have access to through your home schools, but it's really ideal for doing problems like this. But the frowny face says that the math department decided not to use this, again, over my objections. But you do have access through the College of DuPage, being a student here, to Excel 365. So that is a smiley face. And also you have access to TI-84-ish technology. Either you have one or you can go to the Learning Commons and get one. And so these are, technologies that you can use even though we do not have MATLAB at the present. So that's the LSA, but now we're going to give you a little bit of context. Oh, and here is here's the function. It is miniverse in Microsoft 365 Excel, and so this can tell you how to use. And this is a YouTube video that tells you how to do things with matrices in the TI-84. And again, you can get help from Jesse Hayes Carver, me, or anyone else in the Learning Commons on those two if you need help. Okay, so that's the. Okay, now this is the fellow's name, Leontief, and he was born in Russia. He left Russia, and he was fortunate to get out of Russia. They thought he was actually dying, and then he didn't die, so good for him. He got out of Russia and went to Germany. He studied in Germany, but then he immigrated to the United States, and he was at Harvard. He was a very accomplished economist. He won the Nobel Prize in economics in 1973. And I didn't really check this out, but I don't know of anybody who had 4 of their students who also won the Nobel Prize. And it's interesting, one of his students won it before he did, but he had 4 students of his that won the Nobel Prize. A very impressive kind of feat. Okay, in 1949, he used an early computer at Harvard and data from the U.S. Bureau of Labor Statistics to divide the United States economy into 500 sectors. That's actually a very big job. And then he modeled each sector with a linear equation based on data he gathered, and he used the computer, which at the time was the Harvard Mark II that he had access to because he was teaching at Harvard, to solve the system. This is one of the first significant uses of computer for mathematical modeling. And just to talk a little bit more about this noble fellow, he was a very strong component of using quantitative data in the study of economics. And he campaigned against theoretical assumptions and non-observed facts. According to him, too many economists were reluctant to get their hands dirty by working with raw empirical facts. So he did much to make quantitative data more accessible and more indispensable in the study of economics. And I'm taking a little bit of a detour. But the Harvard Mark IV weighed over 20 tons. This shows you the size of it. And in fact, the developers of the Mark II were Aiken, who's a legend in computer science, and someone you might not know about, Grace Hopper. She was one of the first women, and she was a Navy person as well. I think she was an admiral actually in the Navy, but she also taught at Harvard, and she was a co-developer of this machine. And this is an exhibit from this machine. Also is famous, I think, because what happened is the machine wasn't working, and they tore it apart to find out why, and they found this bug that they pasted in there, and that is why the term debugging came about. And I don't know if Grace Hopper actually wrote this notebook, but she could have. Leontief earned the Nobel Prize for his work on things called input-output tables. Now, input-output tables analyze the process by which inputs from one industry produce outputs for consumption or for inputs in another industry. And with the input-output table, one can estimate the change in demand for inputs resulting from a change in the production of the final goods. So the analysis usually assumes that the input proportions are fixed, and then you're using the input-output analysis, and this is limited to rough approximations because there aren't stochastic inputs, but still it was novel at the time and inspired large-scale empirical work. And it actually was very intellectually satisfying because in 2010, its iterative method was recognized as an early intellectual precursor to Google's PageRank algorithm. Kind of a powerful kind of thing. So let's tell it like it was a story. So it was late summer in '49, and he was carefully feeding the last of his punched cards into the university's computer. And the cards contains information about the U.S. economy and a summary of more than 250,000 pieces of information from the U.S. Department of Labor Statistics after 2 years of very intensive work. He had divided the U.S. economy into 500 sectors, coal industry, such as the coal industry, automotive industry, communications, and so on. For each sector, he had written a linear equation, described how the sector distributed its output to the other sectors of the economy. This also was a lot of work. Now, because the Mark II, one of the largest computers of the day, could not handle the resulting system of 500 equations and 500 unknowns, he distilled the problem into a system of 42 equations and 42 unknowns. This required several months of effort to program the Mark II to do this, and he was anxious to see how long the computer would take to solve this problem. It worked for 56 hours before producing a solution. And it's interesting to note that your cell phone has more computing power than the ground-controlled and spacecraft computers for Apollo 11 combined. The importance of linear algebra applications like this is written in direct proportion to the increase in computing power over time. This is called big data. With each new generation of hardware and software, there's a demand for even greater capabilities, and computer science is thus intricately linked with linear algebra through the explosive growth of parallel processing and large-scale computations, and perhaps someday quantum computing. So scientists and engineers today work on more complex than ever dreamed of problems. And this has more potential value, linear algebra, for students in many scientific and business fields than any other mathematics subject. And so, anyway, we'll goes on. Okay, so now finally we're going to talk about his model. Okay, so he says, suppose a nation's economy is divided into N sectors that produce goods or services, and we're going to let X be a production vector that lists the output of each economic sector for 1 year. And also suppose that another part of the economy, called the open sector, does not produce goods or services, but only consumes them. And you might be saying, okay, so these are things that you could export, perhaps. And let D be the final demand vector, or bill of final demands, that lists the values of the goods and services demanded from the various sectors by the non-productive part of the economy. Okay, so all right, so as the various sectors produce goods to meet consumer demand, the producers themselves create an intermediate demand. We'll talk more about this, and sometimes I call this intermediate, sometimes I call it internal demand for goods that they need as inputs for their own production. The interrelationships between the sectors are very complex, and the connection between the final demand and the production is unclear, so he asked, is there a production level, X, such that the amount produced or supplied will exactly balance the total demand for the product? That is, the amount produced will satisfy the internal demand or intermediate demand and the final external demand. So the basic assumption of his model is that for each sector there is a unit consumption vector in Rn that lists the inputs needed per unit of output for the sector. And so all inputs and output units are measured in millions of dollars, and the prices of the goods and services are held constant. Let's see what this looks like. So here is a simple thing where we have a manufacturing sector, an agriculture sector, and a services sector. And notice that it goes manufacturing, agriculture, services, manufacturing, agricultural services. So we always have that. Now, these are the inputs consumed per unit of output. So to make 1 unit of manufacturing output, you need 0.5 units for manufacturing, because most manufacturing things use equipment that somebody else made. So they have an internal feed there. They have to eat, and some of their raw materials may also come from agriculture, and they need to buy money from banks, and they have people who clean their manufacturing facilities and service them, so those are service industries. Okay, so this column, these are inputs consumed per unit of output. And you have the same thing, I talked about manufacturing, but agriculture, they use farm equipment that was manufactured. They have to eat, and they also use seed corn to grow new corn, and they borrow money from banks, as example. And the service industry also depends on manufacturing. They have to use computers, they have to eat, and they also borrow money from banks and things like that. So anyway, you can say, yeah, I could see how we come up with something like this, but note that these are vectors. This is C1 vector, this is C2 vector, and this is C3 vector, column vectors. Okay, so that thing is called the consumption matrix, and so you see that it is here. Now, so what happens is, in order to produce X units of output, you have to, where X is a vector, this consumption matrix tells you how much was internally consumed before you ever get to satisfying an external demand. So this is Cx, is the intermediate demand, or the internal consumption demand, and this is the consumption matrix. So here's the equation, and the amount produced to satisfy this demand, you have to satisfy the internal demand plus D. Now this equation can be written as, if you're thinking about these as matrices and vectors, this is the identity matrix times X on this side. I'm moving this to the other side, that is minus Cx, the consumption matrix times the production vector, and this is equal to D. So this is an important rewriting of the equation, and I think later they'll refer to equation 4, so you'll make note of what that is. Okay, and so that equation 4, which is here, may be written this way, or you can factor the x out this way. We're factoring the x out on the right as a vector, and we can do this, although the multiplication, as you know, is not commutative. So this is I minus C times x equal D. Well, this is a system of linear equations, and remember that the I is a matrix. In this case, it's a 3 by 3 identity matrix, but you're subtracting the consumption matrix off to that, so that calculation has to happen. Let's look at an example, a quick example. Consider the economy whose consumption matrix is given by 3 up here, and the final demand is 50 manufacturing, 30 agriculture, and 20 services. Find the production level X that will satisfy this demand. Well, that's a system of linear equations. And we know we don't have to write all the x's and stuff like that. What we can do is we can look at I minus c, and we can really do, here's I minus c. When you do that calculation, you get this. But then we can row reduce the augmented matrix with the 50, 30, and 20 over here. And so if we do that and do a couple of steps, we get over here. And in fact, this is fully done in Gauss-Jordan reduction. We find that 226 is the amount production here, 119 is the amount of production here, and 78 is the amount of production here. So manufacturing must produce approximately 226 units, agriculture 119, and services only 78. Now, if the matrix I minus C is invertible, and we are talking about invertible matrices in the coming week, then we can apply Theorem 5 with, well, let's just talk about what Theorem 5 says. So you see what we have is that I minus C times X is equal to D, but if we can multiply by, okay, let's just read the theorem here. Let C be the consumption matrix and D be the final demand. If C and D have non-negative entries, and if each column sum of C is less than 1, then the inverse does exist. So this is I minus C whole inverse of that matrix. And the production matrix can be found by multiplying on the left-hand side by I minus C inverse D. So X is equal to I minus C whole inverse D. And that has non-negative entries. And this is the unique solution to this. Okay, now the following discussion will discuss why the theorem is true, and will lead to another way to compute this besides computing the inverse of the matrix. Okay, so this is a formula for I minus C inverse. So imagine the demand represented by D is presented by various indices at the beginning of the year, and they respond by setting their production levels X equal to D. Well, this will exactly meet the following demand, but as they prepare to produce D, they send out orders, and this creates an intermediate demand. And so to meet the additional demand of this, they will need additional inputs in the amount of C times CD, and that's C squared. And that'll be a second round of this. And then it creates a third round as they produce even more. C times C squared is C cubed, and so on. So this couldn't continue indefinitely, although in the real world it would not take place in such a rigid sequence. So anyway, if we talk about this hypothetical situation, we get, and here's a summary of that. So these are the intermediate demands, and you see that each time you're getting C, C squared, C cubed, C to the fourth. And so the production level that will meet all of these demands as they are being adjusted is X is equal to D plus CD plus C squared D plus C cubed D, and so on and so forth. Well, you can factor D out of this, and you will have D times this sum. So to make sense of this equation, you consider this following algebraic identity. And by the way, this is something that comes from, there is matrix algebra, and you actually should be able to prove this yourself using using the matrices. But if you look at this, you say, oh yeah, this truly is an algebra thing. So I minus C times the identity matrix plus C squared plus all the way to Cm is I minus C to the m plus 1. Now it can be shown, we're not doing that here, but if the column sums in C are strictly less than 1, then I minus C is invertible, and Cm approaches the zero matrix as it gets large. So that means you see that this finite sum here approaches the inverse. And so this is the result we were looking to, that I minus C inverse is approximately equal to I plus C squared all the way up to plus C to m. And again, when the columns of C are summing less than 1. Okay. Now in the actual input models that you get, the powers of the consumption matrix usually approach 0 rather quickly. And so you don't have to go too high for M to be a good approximation. And that's in fact a practical way, we'll talk more about that later, to compute the inverse of I minus C. Likewise for any D, the vectors CMD approach 0 quickly. And so this is a very practical way to solve this is that approximation that we just talked about. Now, if the entries in C are non-negative, then the entries in X are also non-negative. That can be derived from the equation that we had above too. Okay, so a numerical note then. In any applied problem, not just economics, that equation can always be written this way, with C equal I minus A. And if the system is large and sparse, meaning there's a lot of zeros in it, it can happen that the column sums are less than 1, and you could solve it this way. And that means taking the sum of these powers of C is a meaningful way to find A inverse, is practical. Okay, now having discussed all that, let's go back and restate the problem. So suppose a 4-sector economy, you've got it here. So there is the consumption matrix, here's your demand matrix, and you want to, first of all, invert this matrix using some of these technologies. Then you want to compute the power matrices up to power 5, add them together, and use that as the approximation and see what happens. So you do A, you do B, and then you do a essay question talking about discussing your observations. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself, because self-care is important, and of each other. Strive to make a difference. God bless you all. Look forward to seeing you in class.